Hi everyone. So welcome to our talk today at the Algorithmic Learning Theory Conference. And today I'll present our work on submodular combinatorial information measures with applications to various problems in machine learning. And this is kind of joint work with Khargonkar, Jeff Bilmes, and Himanshu Asnani. So the outline of the talk is I will first kind of motivate and kind of recall submodular functions, and then I'll actually kind of define the submodular information functions, and in particular then go over different applications, properties, and examples of these functions. And then finally, I'll actually talk about some future directions. So a recap of set functions, right? So set functions appear a lot in machine learning where we want to select a subset of data points, right? So imagine you have a very large data set, right? And you want to select a subset of these data points either to label, right, in the case of active learning, or maybe you want to select a subset of these data points for efficient learning under resource constraints, right? So in either of these cases, you have a very large set of data points and you want to select a subset here marked in red. And this problem is data subset selection for training machine learning models, right? A similar application is imagine you have a very large image collection and you want to select a subset of kind of images here for better visualization, right? So this is a summarization application. So a natural class of functions that kind of model some of these properties is the class of submodular functions. I'm sure many of you are familiar with submodular functions. So submodular functions have what is known as this diminishing returns property that says that the gain of adding an element shrinks as the context of the set grows, right? So here I have essentially a subset A and a superset B, right? And the gain of adding a new element B to a subset is actually larger than the gain of adding this to the superset. A set function is also said to be monotone if the value of the set function grows as the context of the set grows, right? So a number of various problems, like for example, influence in social networks, entropy of a set of random variables, and information gain, etc., are all monotonic submodular functions. So it turns out that a number of interesting subclasses of submodular functions appear and kind of appear naturally in applications. So things like entropy comes naturally in kind of information theory as the information content of a set of random variables. You also have matroid rank functions. You have representation functions like test location and graph cuts. You have coverage functions, things like set cover, probabilistic set cover, and you have diversity functions like log determinants, which are connected to determinable point processes. And you also have concave over modular functions, right? So each of these are kind of natural subclasses of submodular functions. All right. So with this now, we'll actually kind of define these submodular information measures, right? So recall that in information theory, we naturally have these concepts defined already, right? So you have entropy of a subset of random variables here as the expression over here, right? So this kind of measures the information content of this set of random variables. So you can define this either for a single random variable or for a subset of random variables, right? You can then extend this to define the joint information or the mutual information between two sets of random variables, right? So imagine you have two subsets A and B of random variables, and you can define the mutual information between XA and XB, and this is as defined as follows, right? And then you also have the conditional entropy, right? And the conditional entropy is kind of the conditional gain of adding a subset A to an existing set B. And finally, you have the conditional mutual information, which is the conditional joint information between A and B conditioned upon a set C, right? So all of these quantities are known. These are known with single random variables, and these are also known with sets of random variables. So the motivation for this work actually comes from very early work by Shannon and several others who have tried to characterize the entropy functions. And they realized that entropy functions actually satisfy these kind of nice, simple properties, right? And essentially, these properties are that the function is normalized if f of the empty set is 0, right? The function is monotone if f of a is greater than or equal to f of b. And it also has the property of two alternatives, which basically submodularity, that f of a plus f of b is greater than or equal to f of a union b plus f of a intersection b. So this is in some sense kind of fundamental properties of entropic functions. But it turns out that actually you have a more general class of functions that satisfy this, and this is called polymetroid functions, or like monotone submodular functions. And it turns out that actually polymetroid functions strictly generalize entropy. So there's been work in the late 90s, early 2000s, where people have been trying to characterize entropic functions, and they found that actually entropy functions are a strict subclass of polymetroid functions, or a strict subclass of submodular functions. So given this, we can actually try to characterize now a more general class of information measures, which can be defined via submodular functions. So you can define these submodular information functions, right, which are the kind of information functions themselves which generalize entropy, right? But given this now, you can define a few simple extensions. One is the submodular mutual information or the submodular joint information. And this is kind of an algebraic quantity right now, not really the same intuition from the random variables perspective, but now given two sets of discrete quantities, right? Two discrete sets, we want to capture this kind of joint information between them, right? So you have this kind of joint information if of a comma b as f of a plus f of b minus f of a union b, right? Similarly, you can define the conditional gain of f of a given b as f of a union b minus f of b, and you have the conditional mutual information. Okay, so I'll actually skip this. It turns out you can also define the multi-set mutual information, where you can extend this to multiple sets, and we actually define two variations of this. One is very akin to the total correlation, again with entropic quantities, and the second is the multi-set mutual information. So this is an example of the mutual information with two quantities, right? And the kind of a Venn diagrammic way of viewing this. This is a Venn diagrammic way of viewing the multi-set mutual information with three quantities. Okay, so I'll quickly look at a few examples now. So it turns out that you can actually define this with modular functions, right? So with modular functions, these kind of have kind of expected quantities, right? So f of a is equal to wa. You have the conditional gain is nothing but the set difference. The mutual information is the intersection, and so on and so forth, right? Slightly more interestingly, we can actually define this for the set cover as well. And for the set cover, it turns out that it is the weighted set cover on the difference in the concepts, right? So the conditional gain is the difference in the concepts. The mutual information is the intersection in the concept space, and so on and so forth. You can also define this for specific location, and again, this has interesting kind of this interesting expression here, right? So the min of the max expression. So max, recall, is the representation between the two, kind of the representation between the two sets of each item I, and here we are taking the minimum amongst the maximum representations. So actually in our paper, we actually look at a few more examples and few more instantiations of this. Okay, very quickly, I'll talk about a few properties. So these properties are also expected, right? But still you can actually formally show this. So you can show, for example, that all of these kind of measures are all non-negative. This actually kind of directly follows from the definition of these functions, basically polymetroid functions. And you can also show that these are actually monotone. So f of a and f of a given b are monotone. If of a comma b is monotone in one set, fixing the others. And similarly, the conditional mutual information is monotone, right? And finally, we can actually look at kind of upper and lower bounds. So you can show kind of some simple upper and lower bounds now for these entropic, these kind of more general properties. Okay, so with this now, I'll talk about actually one very important result which we showed in our paper, and that actually studies the submodularity of the mutual information, the kind of generalized submodular mutual information, right? But I'll take a slight detour. So recall that monotonicity basically says that the first order gain is greater than or equal to 0. Submodularity is actually the second order partial derivative. The second order gain is less than or equal to 0, right? So this is submodularity. It turns out that you can come up with a subclass of submodular functions which require that the third order partial derivative be non-negative, right? And this is this expression. Okay, so it turns out many subclasses of submodular functions like set, cover, fetch, location actually satisfy this. But what is more interesting is that okay, so the submodularity of f of a and the conditional gain is kind of expected. That follows directly from definitions. But the submodularity of the mutual information is not clear, right? In fact, the standard mutual information over a set of random variables was shown to be not necessarily submodular, right? But it turns out that for certain special classes of submodular functions, this mutual information actually is submodular, right? And this is exactly the case that the third order partial derivatives is non-negative, right? So, however, in general, this is actually a difference of submodular functions. All right. So with this now, I'll quickly spend maybe a minute or so talking about applications. So one particular application is summarization and also subset selection, right? So each of these applications, you have a set of data points. You want to select a subset of these, and you could select different notions of subsets, right? One is you just care about generic subsets, right? Another is you care about this in a targeted aspect, so either with respect to a query or with respect to a certain privacy constraint, right? So I'll look at some concrete examples. Imagine you have an image collection here. A generic summary would be just a set of diverse points from this. A query focused summary is a set of points that are diverse but also relevant to a query person, right? And a privacy preserving summarization would mean that I want a summary that does not contain the word, is not related to person, right? So person is my private kind of information, and I don't want to have person in my summary. Another example is targeted subset selection, where again you want to select a subset of data points that are related to a target set, right? So I'll actually skip this in the interest of time. So it turns out that we can actually formulate this general class of problems, which is maximizing the conditional mutual information, right? Given a query set, the conditional mutual information with respect to a query set given a private set. And this formulation can actually turns out to be related to then each of the individual cases, like say privacy preserving, query focused summarization, and extractive summarization. All right. So with this, I'll talk about some very exciting future directions that I'm interested in, that you know me and my collaborators are interested in, and also hopefully some of you would find interesting. So one is applications towards clustering and diversified partitioning, applications of targeted data selection and targeted summarization, extensions of things like distance metrics, generalized entropy notions, and so on, and also kind of studying the stochasticity. Awesome. So thank you so much, and I really appreciate for your for your attention. And if you have any questions, please let me know.